Okay, so let F and G be maps of cochain complexes on C with boundary operator delta, and to the cochain complex D with boundary operator delta prime. Then, if F and G are chain-homotopic, we'll get to that in a second, then the induced maps of cohomology groups, right, the maps induced by F and the map induced by G, are precisely the same. So before we get into the exercise, let's just recall what all of this means. So if F and G are chain-homotopic, right, that means there exists a map, right, for each object in the chain complex that takes the ith object in the source complex to the I-1th object in the target complex, like that. Right, so the chain-homotopic, if there exists such a map, such that the difference between F and G can be expressed as this thing here. And let's just try to make sense of what this thing is. So you can see this right here. Right? It first performs this one, and then performs the boundary operator, right? The co-boundary operator, I should say. So the source and target of this one are Ci and dy. Same for this thing here. First performs the co-boundary operator, and then this phi map. And same thing here, source and target are Cy and dy. And so since we're working over an abelian category, this is super well defined. So now we can actually do the exercise. Okay, so I've got the definition of a chain homotopy up there, and the definition of the ith cohomology group up there. So one thing that you should notice is that the elements of this group are going to be cosets with representatives in the kernel of the ith co-boundary map. With respect to this set, the image of the I-1th co-boundary map. So a strategy to show that these two induced maps of ith cohomology groups are going to be the same. What we're going to do is we're going to pick one of the cosets and see where it goes under both maps. And we're going to show that the representatives are going to differ by element in this set. So let's see. Let's pick a coset. So we have the representatives from the kernel right there. And let's just put it through the maps. So one thing you can notice that we can put G to the right and then just evaluate in Y to see where the representative gets taken. So once we do that, we notice that we don't know what Gy is, but we do know what this is going to be. Namely, Y is an element of the kernel of the ith co-boundary map. So it's going to be the 0, and then the psi map is not going to matter anymore. And this right here, well, we don't know exactly what element it's going to be, but it's going to be something in the image of the I-1th co-boundary map. That's what we're doing here. And that implies that the difference between F and G under Y is going to be an element of this image of the I-1th co-boundary map. Now what that implies is that the coset, right, under F is going to be the exact same coset under G because they differ by an element in this set. And what that means, right, these are elements of the ith cohomology group on D. What this means is that this coset gets mapped to that coset under F and that coset under G, but those are exactly the same. So F maps the same elements to the same elements in the target as G. So the induced morphisms are going to be exactly the same.